Okay. Gabriele, of course you are fine with recording, right?
Yes, yes.
Okay. You better. And
Do I have a choice?
exactly. So hello everyone, and this is gonna be the N+1 meeting of the Ithaca Fest. It's nice to see you
Really?
around. And today the meeting will have two-dimensional category theory as a theme, and the first speaker of the day is going to be Gabriele Lobbia with a skew approach to enrichment for gray categories. And Gabriele, you can take the stage whenever you feel like.
Thank you, Ivan. Thank you. And I'm very glad to be part of Ithaca Fest also as a speaker. I wanted to start with an apology to the people that already heard the talk at PSSL that I gave or the talk that John gave at CT. I hope that you forgot everything. And also, I would like to apologize because Ivan said that it's about two-dimensional categories, but that was not something that I was told. So this is actually three-dimensional. But it's fine. Anyway, today we'll talk about this skew approach to enrichment for gray categories, and this is joint work with John Burke. It's based on the paper with the same name, which has recently accepted in Advances in Mathematics. So to start, one of the motivations for this is the so-called iterated enrichment idea. And so what is this? The idea is that when you start, you have, like when you start with a monoidal category, B, if it's nice enough, then the category of enriched categories is also monoidal and maybe nice properties as well. So the idea is that you can start with a monoidal category, enrich, and then enrich over the rich categories and go on like this. This is the iterated enrichment idea. And it's, for example, is very useful for strict higher categories because you start with set, then you enrich over set and you get categories, then you enrich over categories and you get two categories, and so on and so forth. The only problem about this is that it's all nice, creates some nice definitions, but the problem is this enough? Can we capture weak higher categories? How can we go with the weakness? So at the start, everything goes fine because one-dimensionally, enriched category, enriched over set is the same as cat. We don't have any weakness, so it's fine. Two-dimensionally, we do have something different because we have bi-categories, which are weaker than two categories, but it's still fine because any bi-category is weak equivalent in a suitable way to a two category. The first problem appears in dimension 3 because when it's not true, unfortunately, that every tri-category, the weak notion of a three-dimensional category, is equivalent to a fully strict three category. Now, fortunately, there is a solution because luckily Gray introduced the Gray tensor product, and which is like a monoidal product, which you can equip the category of two categories with, and then you can enrich over this structure, and you get what are called gray categories, and these are enough, meaning that every tri-category is equivalent in a suitable way to a gray category, which, since they are enriched, they are quite strict, but there is something not strict about them. At some point, it will come up. But it's still nice because we can use a product, a tensor product, which is not Cartesian, but it's still monoidal. So at the moment, it's fine. What is the open problem that we addressed in this paper? Well, the problem is about four dimensions. When you try to enrich, when you try to find a nice tensor product for gray categories. Now, so the question is it possible? Can we find a nice tensor product to go on a little bit like with this idea of going on with enrichment and get something which will be enough in four dimension? The answer is no. Unfortunately, it is not possible to find a monoidal biclosed structure on gray categories, which is nice. What I mean with nice is it's not possible. There are two different papers proving that. First, it's not possible to have a monoidal biclosed structure capturing weak transformations, which is already very not nice. And then secondly, going on a bit with the idea of we want to model weak stuff. So we want something behaving nicely with respect to the model structure that we have on gray categories introduced by Luck. Well, there is, Burke and Gursky recently proved that there is no monoidal biclose structure also interacting well with the model structure defined by Luck. So the answer is no. So it's not possible. Luckily, the talk does not stop here because there will be a solution, but at the start, we will look at what is the problem, like why it's not possible to have a biclose structure capturing weak transformation. So let's assume that we have it. So we have an internal home. I assume you see my mouse. If not, let me know. So we assume we have an internal home, which is biclosed. So we consider a weak transformation, and this should be a gray functor from the arrow gray category into this internal home, just by abstract nonsense, let's say. And by closeness, something like this, you can put 2 inside and then take A outside. You can do a little bit of biclose magic, and you get that this thing should be the same as, again, a gray functor from A to this internal home between 2 and B. So what is this thing? This thing would take a map, an object, and assign a map, which would be something from 2 to B, and then a map will be sent to a square. Okay, at the moment, no problems. What is the problem? The problem is the functoriality in A, because functoriality would force something too strong for something three-dimensional. Because functoriality would mean that if we take 2 composable one cells in A, and then we glue together these 2 squares, which correspond to F and G, then these should be equal to the one corresponding to the composition, so to this one. And this is very unnatural in higher categories, and actually this would mean that weak transformation would not even be composable, which obviously is quite annoying. So what we would want and what would solve somehow the problem is, instead of having an equality, having an invertible free cell. This is something that happens quite often in higher dimensional category theory, where we replace identities with invertible free cells. Now, how can we solve this problem? So the idea is that we, instead of having something strict, instead of having something like a gray functor from A to this internal home, we want something weak, because again, the functoriality shouldn't be strict, but should be somehow pseudo. So the solution that we found was to consider Gola's mapping space for gray categories. So Gola, in his paper called, I think, something like Mapping Space for Gray Categories, exactly, introduced this notion of pseudo maps for gray categories. So the nice thing about them is that locally they are strict because they are a true functor. They also are normal, meaning that they preserve basically all identities. The only non-strictness of them comes from the fact that composition of one cell is not preserved strictly, but we have this co-cycle. So we have this invertible true cell satisfying some conditions. But that's the only non-strict part, let's say. And I mean, again, obviously these will come up in the axiom, but the idea is that the only non-strict part is here. Just a little warning, which we will solve, but the problem, and again, like you might wonder, oh, we have this internal home, maybe we can find a representing tensor. Well, weak maps usually are not super well behaved, so it's still unlikely. We could try, but it's still unlikely. So I'm trying to convince you, and I mean, there are a couple of papers about the fact that monodal is not the way to go. So you might wonder, well, if not monodal, what can we do? So just to remind yourself, what we want is something encoding the notion of a weak map together with a tensor product and also an internal home. So we want basically all of these characters interacting with each other. The solution is skew monoidal categories. So closed meaning that we will have the internal home. But focusing on the skew monoidal part, just for those of you who don't know, they're not crazy. They're just, imagine a monoidal category where the associator, the unitors, instead of being invertible, they're just one cells. There are cells going from one bracketing to the other. They're not invertible. It's important, the direction, for reasons that I will not mention, but if you're interested, you can ask me a question at any point, or we can talk later. Anyway, why are skew monoidal categories the right notion? So first of all, in skew monoidal categories, we do have a notion of weak map, because we can consider weak maps as maps from the unity of this monoidal product in tensor A into B. And these are somehow weak in some sense. We do have a very simple notion of closeness, very similar to the monoidal case. And yes, the idea is that this map is not invertible anymore because the unitors are not invertible. And so we do have this notion of weak map different to the standard, let's say. So this brings us to our main result of the paper, which is that we proved that there are two closed skew monoidal structure. Actually, we proved more. Spoiler, there will be also more in this talk. But the main two that we proved are these Lux one, so this Lux gray product for gray categories, let's say, which is this closed skew monoidal structure capturing this notion of Lux transformations introduced by Gola. And then we have another one with internal home, this pseudo transformations, let's say, which we introduce, but they don't differ too much from the Lux part. It's just we have an adjoint equivalence where before you didn't, things like this. And the nice part, and these replicates somehow the pseudo gray product. And the second one is also symmetric, as we will see. So it's quite nice. So that was the main result, but how do we get there? Because obviously defining this product could be hard. So we could go through different. We do have different options, let's say, because similarly to the no skew case, where we have monoidal categories, then multi-categories, when they are presentable, they're equivalent to monoidal categories. And similar, we also have closed categories where we axiomatize things based on the internal home and not the tensor. So something very similar happens also for skew. Under certain conditions, these three notion of skew monoidal, skew closed, and skew multi categories are equivalent. So basically you can choose whichever is more useful for you. So let's start. Why not skew monoidal? Well, skew monoidal could be a bit hard because defining the tensor and then proving the axiom could be a bit hard. So maybe you wonder, well, if not the tensor, maybe we could define the hom, because the hom is already defined by Gola, so that could be easier. And usually it is easier to define, but in what on this monoidal part is the associator in the closed case becomes this L. This L, which goes from an internal home to the internal home between internal homes and blah, 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 which, trust me, becomes very hard to manipulate. It's not impossible, it's doable, but it's not ideal, let's say. So, I mean, it's the last one, so you can imagine that actually what we chose was skew multi-categories. Why did we choose that? We chose that because the idea is that instead of defining directly the product, you define it through a universal property. A bit like when you define the tensor product for modules, you don't define it, like you can define it directly, but you can also define it through the universal property through bilinear maps, which is quite nice, and that's the somehow our approach. And the only problem about the skew multi-categories is that as multi-categories, we would need to define n-ary multimaps and check a lot of axioms for all natural numbers. The solution to this problem was given by John's work with John and myself in my PhD thesis at the last chapter, I think. And the idea is that actually, under certain conditions which are satisfied in our case and are satisfied in a lot of cases, it is enough the Fourier structure, which I will explain in a second. But the idea is that instead of needing for all n, you just need the structure up to dimension 4. So it's quite nice because you have like a finite number of things that you have to define, and it's more controllable in some sense. Okay, so what are skew multicategories? Skew multicategories were introduced by Burke and Luck in 5 years ago. And as a multicategory, they have objects. They have nullary maps, which I label L and it will be clear next slide, probably. And then we have n multimaps for any n, which I will call loose at the moment. So at the moment, we only have the structure of a multicategory. But then the skew part consists of adding these tight maps. So choosing a subset of these loose maps, which we call tight. And again, the idea is that they need to be a bit more strict in some sense. Again, next slide, I will give an intuition about how to interpret these tight and loose. And the identity must be also inside these tight maps, which makes sense because the identity should be quite strict. Then we go basically like a multi-category, because then we have substitutions where we take an Emery multimap G and F going into BI, and we insert inside, and we do this for every I, for every N, for every M. And these have to satisfy some unit and associativity laws. The only, which are the same as multi-categories. The only different thing is that we basically need to say when these substitutions give something tight. So the rules are here, but I will explain them in the next slide. I'm referring to the next slide maybe too much, but it's coming, don't worry. And the rules are that if G and F are tight, then the resulting map is tight, because the idea is that the first component, like the tight maps should be strict in the first component somehow. And so also if G is tight and F is inserted in any place that it's not the first one, then the result also needs to be tight. I was talking about Fourier structure. So let me just mention that K-ary for K and natural numbers, skew multicategories, are the same as what I just described, where we stop at dimension K. So instead of defining for any n, these tight and loose n-ary multimaps, we define it for n less or equal than K. And then also substitutions, we need that the resulting map has to be less or equal than K. As promised, finally, this understanding of tight versus loose. So the example that I think it's good to keep in mind is the example of the category of categories with a choice of finite product. Loose n-ary multimaps at that point would be functors from the product of A1, AN into B, which preserve the products up to ISO. And instead, the tight n-ary multimaps will preserve the product up to ISO everywhere, except in the first variable where they have to preserve it strictly. So the idea is that tight maps are strict in the first variable, which then makes you understand why if I insert F into G in the first variable, then, well, if F is tight, then it's strict, then I follow G is still strict, and so the resulting thing should be strict. And as you might have noticed, nullary maps instead are just loose. We don't call any nullary map tight, exactly because when we insert a nullary map inside a tight map in the first variable, well, the first variable of F disappears, and the first variable of the resulting thing is the second variable of F, which we did not know anything about. So the resulting map should be loose. Okay, if there are any questions, please interrupt me. If not, we go on, and I will try to give you a bit of intuition on the skew multi-categories that we described. Because as I was mentioning, instead of defining directly the tensor, which as a point we do give in the paper a description of the tensor, but our approach of proving that we have a skew monoidal structure is proving that we have a skew multi-category, actually a skew Fourier multi-category, both in the Lux and pseudo case, prove the couple of properties that we need, and then we have a skew monoidal category. So the null maps are easy because we take, so yeah, I didn't mention it maybe, but the objects of our skew multi-categories will be gray categories. So A is a gray category, null maps are just objects, as most of the times. Then unary maps, the loose maps will be these pseudo maps introduced by Gola, and the tight maps, the gray functors. Now, how do we find binary, ternary, and Fourier? The aim of this slide is trying to convince you that it's not crazy because we go a bit inductively. So we build up. So we start with a binary, and then we build the next ones. So we start with binary, and again, the idea is that we already know that we want to construct something close. So we want to define a binary map somehow connected to these pseudo maps from A to Lux BC, which is this mapping space of Gola. So following these, for example, if you start here, you will have, like, just think about the assignments from any object A. You will need an object of Lux BC, which is a pseudo map from B to C. For any one cell, you will need a one cell in Lux, so a Lux transformation. And well, as easy as that, we do get that. So the nice thing about binary loose maps is that we can give a very compact description, which as data, we literally only have these four things, which are for every A, a pseudo functor from B to C, for every B, instead another one from A to C. And then on one side, a Lux transformation, on the other side, very dually, a not-Lux transformation. And then these have to satisfy some axioms, some compatibility axiom, and a couple more. And yes, the tight maps, again, to understand it as strict in the first variable, FB, so when you look from A to C in the first variable of F, then these must be a gray functor, plus some more condition, but that's the main condition, let's say. Now, this was for Lux. For pseudo, it's not crazy, the difference, because the only thing that we get instead of having a Lux transformation and a not Lux transformation is that we have a pseudo transformation and a pseudo transformation, which gives you also an intuition why this structure instead will be symmetric. Now, instead, as I was saying, ternary maps we should be able to define ternary map using binary map. And actually we are, because ternary map turns out to be just the data of 3 binary maps. So one for every A, we will have a binary map from the other 2, for every B, from A to C to D, and blah, blah, blah. And so we have 3 binary map, for every object's 3 binary maps, compatible with each other, plus a free cell, this HGF for one cells like this one in A, this one is in B, and this one, not surprisingly, in C. And these 3 cell, which we call incubator because the idea is inside a cube, whatever. The idea is that it tells you how these 3 binary maps interact with each other. And again, we have axioms, but it's nice, like it's already something, because we see binary are 2 unary plus stuff, ternary is 3 binary plus stuff, and then when pseudo, you do get 3 pseudo binary instead of Lux binary, and you also get that these 3 cell must be invertible. But then for Fourier, you get also something very similar, because binary was 2 unary plus blah, 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 ternary 3 binary plus blah, blah, blah. Fourier is 4 ternary plus nothing, but an axiom. So the nice thing is that, and this is a bit of a coincidence, but for Fourier maps, we don't have any more structure, just an axiom, saying that these 4 ternary maps interact well with each other. Okay, now coming to the properties of the pseudo product that we have. So first of all is right normal, and which is nice categorically. which means that if you tensor on the right with the unit, you still get something isomorphic. It's nice because it captures these weak maps. So the maps, as I was saying, that should be the weak maps in a skew monoidal category. These from the tensoring on the left. They are indeed the maps, the pseudo maps described by Gola. And this is not in the paper, but it's in a follow-up that we are currently writing. It is also symmetric and it's quite nice. And to prove this is actually useful to have the k-array description, the 4-array description in this case, because in that case, the axiom that you have to prove for a skew multi-category to be braided or symmetric, they reduce a lot. And this is not in my PhD thesis, but will be in a preprint very soon, hopefully. But still, we proved that it's symmetric. The only problem and the only annoying part about this product is that it's not homotopically well behaved. Unfortunately, this product does not preserve cofibrant objects, and so it does not interact well. But as I was saying to you at the start, we do find something that is homotopically well behaved. It's not this one, unfortunately, but is the next one. And this, again, is in the paper. So in the paper, we also define, starting from this skew monoidal structure, we define a sharp version of them, which capture, instead of these pseudo maps of Gola, the strict maps. And this is nice because it's right normal, as the previous one is also left normal. It's not symmetric, unfortunately, because adding this sharpness does present more strictness, but also takes away the symmetry in a weird way. And again, the properties of this one will be studied in the follow-up. It's not symmetric, but it is homotopically well-behaved. And this is quite nice. And the idea is that it preserves cofibrant objects, has all these properties that I wrote, but the real thing that happens, that it's the reason why it's homotopically well-behaved and why it's nice, is that it does induce a skew monoidal closed structure on the homotopy category of gray categories under Lux model structure. Nice. So as I mentioned at the start, one of the motivation for this was to try to think about enrichment. So try to go on and enrich over the structure that we would find. So let me try to convince that the semi-strict 4 categories that we find, which is very long, it's very long, I know, but let me try to convince you that they're not as bad as they sound. And it's not crazy what's going on. It's interesting, but not crazy. So just to remind you, when we go from 2 categories to gray categories, what's going on, what's happening? So the idea is that in a 2 category, for 2 cells, horizontal 2 cells, let's say like this, we have the interchange, which means that we can do alpha or beta in any order, and it's equal the result. So what happens in a gray category is that this axiom is replaced with an invertible 3 cell, satisfying 4 axioms. 4 very reasonable axioms like composition, naturality, something like this. Now, what's going on in our semi-strict 4 categories? So if you enrich, both if you're enriching the pseudo tensor product, as I wrote here, but also if you're enriching the sharp tensor product, which is the one homotopically better behaved. So we believe that probably that's the better definition in some sense for semi-strict 4 categories. But even if you enrich over this pseudo product, then what you get is that you start from this 4 axiom, then the interchange has to satisfy, and magically they become invertible 4 cells because we're going 1 dimension up. Obviously, it's not as easy as this, because it's interesting that actually one of these axioms, especially in the sharp case, becomes just the identity instead of being an invertible 4 cell. And some of them, the co-cycles will appear, so they are not exactly the axiom, but they are the axiom modulo these co-cycles. But it is very similar. It is very similar, not the same again, because if you just put invertible 4 cells, you don't get what we get, but it's not that far off. So it's quite interesting, I think. So just to wrap up a bit, Well, a couple of final remarks. So just to mention that if you start with something sharply enriched, let's say, so enriched in this sharp tensor product, then the opposite category is not sharply enriched, but it's only pseudo-enriched. This is connected to the fact that sharp is not symmetric, and so the strictness on one side gets lost. Also, let me mention that the strictness on one side kind of makes sense, because if you think about when you are, so it's connected to the idea that if you consider weak maps, let's say, pre-composition and post-composition with weak maps behave a bit differently. Usually, pre-composition is less strict, stricter than post-composition. So that's the reason why it makes sense that we don't have something symmetric, maybe. Then, okay, so these sharp, this pseudo, everything else, we have defined it using skew monoidal categories, but we could also have enriched in skew multi-categories. And there is, I guess, a question whether this is a good idea. I don't have an answer yet, but it's definitely something that maybe we could consider instead of going with this iterated enrichment. Maybe skew multi-categories could be helpful, but I generally don't know. It's just something that I thought could be good to mention. And connected to this, I wanted to mention that I don't have a good intuition about the product, like how to continue with the product, let's say, but the multi-categorical structure, some intuition is present, because as I was saying, the fact that in this case, the Fourier multi-maps were the ones where we had only 4 ternary and just with axiom, without data, is a coincidence with the fact that we just need Fourier structure to get a skew monoidal category. But it comes from the fact that we have something 3-dimensional, like gray categories are 3-dimensional. So at some point, you cannot add any more data. And so the idea is that when you have n categories, the idea is that you could go up to n, keeping adding like n-ary multimaps, adding structure, but then at n+1, the multimaps should be only systems of n-ary multimaps with some axioms. But yeah, and here I just wanted to remark that this is the idea, but if you have left representability or closeness, which are the nice conditions that I did not mention, but I vaguely said, then it is enough to define n-ary up to 4. So we wouldn't need to go define up to 7 if we want to define 7 semi-strict 7 categories. But this intuition still might be useful. Thanks a lot for listening.
Thank you, Gabriele. And now we move to questions. We have Nicola is coming, and we shall virtually clap to your talk. Now we have question time, and we have time, I would say, for 1 question and a half. So if you have question, you can unmute yourself and ask your question. Nicola?
If you look at the Bayes-Dolan periodic table and look at the degenerate cases of your semi-strict 4 categories, do you get anything interesting in terms of monoidal 3 categories or things of the sort?
Good question. So the answer is we haven't proven it yet. We will put it in the next paper, but here there is a bonus. We have already compared our notion of semi-strict 4 category with other notions like Kranz and Miranda's ones, and they should be very similar to Miranda's one. And I believe that Miranda compares his degenerate cases to those, like to braided 2 category, for example, and things like that. And we believe that probably we do get what you expect, like a semi-strict 4 category in our sense, with 1 object and one cell, should be probably a braided monoidal 2 category. Again, we haven't proven it yet, but we suspect that probably yes. It's something that we will check.
Thank you.
Thanks, Nicola. And I think we have time for another question because we are 5 minutes late, and that was how we started. So if there is another question, we can take it. Okay, if there are no more questions for Gabriele, thank you, Gabriele, for your talk. And I think we can start moving to the next speaker, who is actually Nicola.